ahead and get started. Thank everybody for joining us today. It's my pleasure to introduce Brian Kahn, who's been a colleague and a friend of mine now for several years. We should probably try to figure out how far back we actually go here in the field, but it's been a long time. We've worked together in the past on CloudSat and Calypso-related work, some of which you've seen me work on. Brian also does an awful lot of work using the AOS sounder, which I know many of you, especially the people at SIMS, are very familiar with. So started off, I think, doing some water vapor retrievals. Since then, you've become the lead developer for the AOS cloud products, and are now exploring creative ways of analyzing the AOS products to understand properties of deep convection, and as well, I think, maybe improve forecasts of deep convection. I want to give you just a little bit of background. There's one really interesting nugget here. So Brian got his bachelor's degree in meteorology from San Jose State University and his master's and PhD in atmospheric sciences from UCLA. And so, at first glance, he's a California guy. And I was, kind of always joking with him about, oh, you'll never survive a winter in Madison or anything. But if you look buried a little bit further deep down in his CV here, you find that he was actually an exchange student in Ekaterinburg, Russia for a full year. So he's actually been through a winter that's probably even worse than anything we experienced here.
It was.
Yeah. So you can trust anything he says. He's got that, he's got that sort of winter experience in him. And actually along those same lines, one of the things that brings Brian here now, and actually in a couple weeks' time, is he's also a co-investigator on my pre-fire project, so my CubeSat project that, again, probably most of you have heard about since I've talked about it a couple of times here as well. Today, though, Brian's focus is going to be more on the AOS research and what can the AOS tell us about deep convection. So thank you, Brian.
Awesome. Thanks a lot, Tristan. Thanks to everybody for coming to the talk. So I guess the best way to start this is I'm really a NASA guy, and my religious doctrine is the Dekado Survey that was just released. And so we have to think about what sort of measurements we need to make in order to do the science we want to do. And I thought this was a good example of how it sets up what I want to talk about today in this 2018 report. If you pick up this question in the weather area, question 4, it's about convective storms and formation processes. And the question is, why do they, how do they form, what sort of heavy precipitation and clouds, why do they occur, exactly when and where they do? And then it discusses vertical motion, how important it is to measure vertical motion. We don't do that currently from space right now. And then you look at this list of all sorts of variables that are required in order to address this, not just the vertical velocity, but condensate, vertical profiles of winds, and then you get down here to water vapor, so 3D water vapor. And you have a closer look at this, and it says things like vertical resolution 1 kilometer, spatial resolution 500 meters, temporal resolution 15 minutes, accuracy half a gram per kilogram mixing ratio. And we're going to get this from infrared hyperspectral that already exists. So I'm pretty sure that we can't do this right now. Maybe I'm wrong, but it sounds like we have some work to do to look at the program of record that's assumed in the NASA's Dekado Survey. So this is kind of my motivation. This is the motivation for the thermodynamics, and there are similar motivational slides I can make for the cloud hydrometeors, but I'll save us the time and the pain on that. Okay, so I'm also not only a NASA guy, but I'm a hyperspectral infrared person, and it's quite possible these are the wrong tools for the wrong job. In fact, I think to a large degree they are. The spatial footprint is large, on the order of 15 kilometers at nadir view. We cannot observe inside of and below thick clouds. The temporal resolution is too coarse, and we tend to be sensitive to the wrong variables or the right variables in the wrong places. So sounds like I should do something else with my life, but I'm going to give it a shot anyway. I will focus on two topics today. They're centered around the AOS instrument, and I am going to use some data from MODIS and also AMSTER-E and AMSTER-2 and a little bit of CloudSat, and I think hopefully motivate some further research on what we could do with what we have now. Okay, so I listed quite a few disadvantages with infrared sounders in order to address what I think are important questions regarding convection. Now, one advantage that we have is that there's lots of data. And here's a typical swath pattern for the ascending part of the orbit. You can see the swath width here. There are gaps at low latitudes because the swath is not wide enough to fill these gaps. If it was at a higher altitude, you'd be able to fill these gaps. So there are approximately 324,000 temperature and water vapor soundings a day with the standard NASA retrieval. Now there are different retrievals that are done here at the University of Wisconsin and SSCC, as well as other research projects that are doing single field of view retrievals. But these are the standard NASA soundings, and there's several hundred of these, there's thousands of these per day. There's about 2.9 million spectra per day, and over 2,000 channels per spectrum. So we have 7 billion observations per day. That's a lot of data. We better able to should do something with it. Now, the history of these observations actually go back many decades, and here at the University of Wisconsin, it's sort of the center of satellite meteorology. And these instruments were flown on aircraft as well as based at the ground, making these types of observations decades ago. This is a really nice paper by Steve Ackerman that he published 30 years ago showing how cloud type affects the infrared spectral signatures. And you could see, the thinner clouds tend to be warmer. You see colder clouds here associated with thick cirrus, and the slopes of the spectra are affected by the cloud type because it tells you something about the microphysics or the phase of the cloud. So these are typical spectra from the AOS instrument, the CRIS instrument, and the EASI instruments, also a very similar type of spectra. And this is a granule in the South Atlantic where I've taken a few pixels and color-coded them up here. So clear sky is in orange. Low cloud right here is in green. Thin cirrus is in red. Thicker cirrus here is in black. And then deep convective clouds, or at least thick anvils here, are in this lighter blue. And you can see as the clouds get thicker, the brightness temperatures get colder, but there's some really interesting spectral features here that we can exploit. The ups and downs are caused by optical thickness variations as well as the cloud top temperature. And then these slopes in the windows are caused by ice cloud particle size changes as well as cloud phase. So you can see here that the thin cirrus in red and the low liquid cloud here in green have opposite slopes. You can see how they sort of trade spaces here depending where you are in the spectrum. So these are the types of features in these spectra that we're exploiting through our retrievals to actually obtain these properties. Okay, so instead of spending a lot of time on the algorithm details, I figured I would just sort of jump to what we did, and we could discuss in the discussion if you'd like to discuss how we actually do the retrievals in more detail, we can do that. But I also want to stress that a lot has been done already from these types of observations with regard to convection. People have looked at deep convective clouds, so the coldest cores of convection relative to the anvil areas and what their ratios are, their spatial temporal characteristics. Claudia Stubenrock's done a lot of work on this in the last few years. People have looked at water isotopes and how they're related to precipitation processes. Data assimilation was a big motivation of the AIRS instrument, and it has improved weather forecasting as well as all the infrared sounders have. They have been instrumental in improving parameterizations in climate models, especially subgrid physics. And then more commonly, people have used the level 2 cloud top property retrievals to look at how clouds vary in their types. And then also environmental soundings around convection. So I just want to touch on these two topics here in these two areas in the bottom. And that's what I'll follow with here for the rest of the talk. So regarding that first topic in the level 2 retrievals, I would like to touch on the ice cloud effective radius. So I think this is a pretty interesting variable, and hopefully you'll find it interesting too. I think it could be a tell for dynamics or some microphysical process pathways within convection. I'm kind of speculating, but I think there's indirect evidence for that. And then another aspect of this is enhancing the time component of these observations. Instead of just looking at a snapshot at 1:30 a.m. and p.m., but actually stretch out before and after the overpass and sort of tease out this information using trajectory modeling and other observations or model results of winds. So with respect to the first subject, here's what a granule map of these different products would look like. In the upper left is a window brightness temperature. Here is the ice cloud top temperature retrieval from AIRS. This is part of a 3-parameter optimal estimation retrieval that the heritage is actually based on the TESS algorithm. So Kevin Bowman and John Warden and others on the TESS project really are at the core of the algorithm that this product comes from. Here is ice cloud optical thickness. And then here's the ice cloud effective radius. And you can see there's little holes and gaps in here, and there are reasons for this, and I've tried to do a careful job of QCing out problematic retrievals. So the ice cloud effective radius is very sensitive to the slope. We know AIRS has several different detector modules on it that are cross-eyed, so they actually see slightly different scenes. And so sometimes the spectra have little offsets based on how heterogeneous the scene is. So this actually could cause an adverse impact on the effective radius retrievals, and a lot of these dropouts are due to that.
Brian, what's the ice cloud effective diameter? What does that mean?
Oh, so it's the ratio of the volume to area of
For an ice particle?
Yeah, but over the distribution
Okay.
of ice particles within 15 kilometers, which just could be an incredible variety of habits and sizes and so forth.
Well, can I ask you a follow-up?
Yeah.
How do you expect that to tell you anything?
It's a great question.
Okay.
Hopefully I'll show you some reasons why
Okay.
I think it should tell us something.
Okay.
But a lot of it is correlations with other data, like rainfall, wind speed, column water vapor. You see these interesting relationships that pop out. So hold on to your question and ask it again later if you feel like it hasn't been addressed.
Thanks.
Okay, so I won't go into how we assess cloud phase, but we use spectral differences between different channels, and it turns out about 26 to 27% of all AIRS pixels have ice in them. 16.2% are liquid, and then about a third definitely have clouds, but we can't identify the phase. Okay, so a lot of these unknown may actually be mixed phase or super cooled liquid, and our algorithms aren't sophisticated enough to deal with these clouds yet. Okay, so basically cloud B comparisons to AIRS shows very good agreement for single-layered homogeneous ice clouds, and then we have poorer agreement, as you would expect, in multi-layered or horizontally or vertically stacked mixed phase. So I would argue that air's ice detection is fundamentally more sensitive than liquid, so producing an ice microphysics product, I think, is more rooted in reason than liquid retrieval. So these are some results where we have matched pixel by pixel the air's cloud phase to CloudSat 2B cloud class cloud typing. So here's deep convection, cumulus, stratocumulus, stratus, altostratus, altocumulus, and then this is just the general cirrus category. So there isn't a cirrocumulus and cirrostratus, it's just one single cirrus category. All the blue little tick marks here that you see are when positive ice tests were triggered in the air's phase retrieval. So it's good that you see a lot of blues for cirrus clouds. It's also good that you see a lot of blues for cumulonimbus. It's also very good that you see some unknowns and reds for altocumulus that tend to be dominated by liquid phase, while altostratus is dominated by ice. So it kind of passes the sniff test. Note that there's a stratocumulus category here, there's ice detection. This is because we use the radar-only cloud classification, so it does not have the thinnest clouds that Calypso would see. Here are the mean particle sizes for these conditions. They're largest for cumulonimbus, cumulus clouds, smaller for these mid-level clouds, but remember these are just the ice cloud parts of these cloud types, not the liquid. Cirrus clouds are a few microns smaller than cumulonimbus, and we have retrievals, as I mentioned, over stratocumulus because there were some missed thin cirrus detections. So, you know, there's several microns of difference in these different cloud types over 2 years worth of data. So I think these are significant. The optical thicknesses also pass the sniff test. Cumulonimbus, you see about 5.5. Cirrus is lower. There's some interesting differences here in altocumulus versus altostratus. Nimbostratus is about half that of cumulonimbus, but we know nimbostratus clouds are very thick and opaque, but they just have a very tenuous upper layer. So it tends to retrieve a lower optical thickness just because there is a thermal contrast implied by a very thin cloud top. Okay, so is the current pattern in time change of ice cloud effective radius from air is reasonable, quote unquote? Well, here's a pattern, a 16-year average of the retrieval, and it's pretty neat. You see structure here. You're tempted to say the particles are larger in this sort of convectively dominated Eastern Pacific ITCZ. Here in the Western Pacific, much smaller particles where thin cirrus dominate the statistics. Some interesting storm track differences on the warm sector side. The particles are much larger than they are to the north, or the poleward side. Over the poles, they're quite a bit smaller. There's some interesting diurnal effects. You can even see some hints of Lee wave clouds where the particles are smaller here. In New Zealand, the Lee of Tasmania, and also in the Andes. And if you look closer at the data, you'll even see stronger signals of this if you isolate on those cloud types.
So your hypothesis about the East versus West Pacific has to do with the amount of cirrus?
I think some of it has to do with the cloud types that occur there. That's my speculation. I'll dive a little bit deeper into looking at AMSR rain rates and wind speeds, and we could have a closer look at thin cirrus versus thicker cirrus, and if there's still those differences pop up. Okay, so another slide that I could spend 10 or 20 minutes on, but I just want to give you a taste here that we have looked at the secular trends in these data over a 14-year period. We published this last year in ACP. Bottom line is that in the tropics and these 18 to 54 degree north and south regions, so southern hemisphere is 18 to 54 south, northern hemisphere is 18 to 54 north. I don't have the polar results here on this figure. So particle size is going up everywhere. No matter whether you use a combined infrared microwave version of the retrieval or whether you use just the infrared-only version of the retrieval. It also doesn't matter whether you use just the middle third of the swath. That's what iron-nator means here. So particles are going up about a half micron over this 14-year period. These vertical bars that you see here are 95% confidence intervals. The inner tick marks are just straight up 95%. The outer tick marks account for the lag 1 autocorrelation in the monthly time series. Okay. Also, optical thickness is going down in the extratropics, but that's a whole other separate story. There are trends in the retrieval parameters, like the averaging kernels that we report. You'll see trends depending on the latitude, but a deeper look at this suggests that the averaging kernel trends really don't have anything to do with the physical trends. So I think that's a good thing. You don't want to see your retrievals follow, say, the chi-squared fit pattern. That would be an alarm bell. Or you don't want to see your patterns fit a trend, say, in a physical property in one thing. For instance, the optical thickness pattern, you would hope doesn't look like the effective radius pattern. In one case, the averaging kernel of the effective radius actually looks pretty similar to the optical thickness, but we know that should be the case because the effective radius sensitivity is actually dependent on what the magnitude of that optical thickness is. So we've dove into this, and the details are in the paper if you're interested.
What do you mean by averaging kernel trend? Do you mean amplitude or change in the peak of it, or what do you mean by a
Oh
trend?
yeah, so good question. So this is just a 3-parameter retrieval where we look at the averaging kernel of the 3 parameters. So there isn't a cross-correlation between, say, temperature, water vapor, or anything like that. It's basically just a really raw measure of the information content of a single parameter.
Okay.
And these look different than the trends of the properties themselves. Okay, some other corroborating evidence I think should be mentioned, and I could discuss these in the backup slides if you're interested. It turns out the MODIS and AIR's ice cloud optical thickness trends are very similar, and they're completely different instruments, so that is quite fascinating. The cloud effective radius tends to be a little smaller over land, both in AIRS, and also this interesting paper by Steve Sherwood about 20 years ago showed something very similar of ABHRR. GEOS 5 and Cloudset Calypso 2C ice also shows smaller values over land. And then there's some evidence of increasing cloud effective radius in NICOM simulations that they said that they found this in the paper, but they actually didn't show the results. And I tried contacting them, and they never followed up with me. So somebody needs to do simulations of ice cloud properties in a future climate and have that as a benchmark for us to evaluate with observations. Okay, so this is just real basic, simple stuff here. All I'm doing is I'm correlating the cloud effective radius at the tops of convection in these next few slides. So this is some previously published work using the Darwin ARM site, where they have an average effective radius profile, okay? And then they divided all the data up into 4 regimes. What they called a convectively active deep cloud period, a convectively active cirrus period, suppressed, and a mixed cloud regime. The bottom line message I want to get across here is during the convectively active period, you can see the particles are about 1 to 2 microns larger at most altitudes in this regime. It's also true in the convectively active cirrus, and then you see the suppressed regime where they're a little bit smaller. So depending on how much convection there is, it seems like there's some variability in the particle sizes. And there are actually a number of papers that have shown similar results. So I won't spend a lot of time addressing those. Now, There are some common explanations of larger particle size at the tops of convection versus adjacent cirrus. And you'll see things like, for instance, liquid of convective origin has a larger cloud effective radius than in situ forms, say, from gravity waves. You'll also hear that large particles are lofted magically upwards in strong convection. I guess in principle this makes sense, but I've never seen a really rigorous argument for this. There's also arguments about enhanced radiative cooling of a thin cirrus layer above deep convection, and this could drive particle growth. So Graham Stevens published a paper a long time ago on this topic. And then you'll see things like changes in vertical velocity can modulate the ratio of heterogeneous versus homogeneous nucleation. So there are a lot of recent papers on this. If you read the hundreds of papers by Danny Rosenfeld, he likes to talk about these things too. So there's a lot of explanations potentially in why particle size might depend on the convective intensity. Okay, so one thing I did, and this is in that ACP paper again, if you're interested in more detail, is we were interested in this Stevens mechanism of radiative cooling impacts on particle growth. So Hani Takahashi, she's very skilled with using CloudSat data, so in like 2 days she created this plot. I don't know how she did it, but she broke up thin cirrus in a very narrow bin, about 190 to 200 Kelvin, and that cirrus had to be very geometrically thin, about 1 kilometer or less in thickness. And then what she did is she looked at just thin cirrus without any clouds below it, and then she looked at deep convection, which had a 10 dBz contour lower than 5 kilometers, and then she found deep convection that had a dBz contour of 10 above 10 kilometers. So this was a proxy for no convection, weak convection, strong convection. And what we found is that the particle size seems to go up from just this thin in situ cirrus to weak convection to strong convection. And what you see here in these dark boxes, this is DARDAR data. So that's data based on combination of CloudSat and Calypso notice. So they both seem to show sort of a similar upward trend here with convective intensity approximated by CloudSat. So we also looked at, okay, what if it wasn't just a thin cirrus? What if you just had strong versus weak convection? Well, you see the same thing. So, I mean, it's really hard to argue that the Stevens mechanism explains this, because there's actually a lot more convection that doesn't have a thin separated cirrus layer above it than just deep convection getting near the tropopause. But there's still very interesting differences between weak and strong that I still don't have a handle on, but I'll just walk you through a few more things here. Okay, this is a really interesting paper. I randomly came across this paper. I got, I think, my AMS alert for journal Atmosphere Ocean Technology. And then I saw this field campaign in the Western Pacific that they're summarizing called HIWC. I think like Ed Zipser and others were involved in this campaign. And what they did is they flew through different types of convection with high ice water content, because they want to understand issues regarding icing in aircraft. So they have these 2 plots in the paper where it shows the total water content here in blue, and the mass medium diameter here, which is like the effective radius, in black. And you notice in this particular cross-section, as the total water content goes up, the particle size goes up. As the total water content goes down, the particle size goes down. And so there's this positive correlation between the two. Well, it turns out this may be a good example of vapor deposition onto ice crystals, and it's a depositional growth piece of evidence. Now, the one on the right, it's opposite. As the total water content goes up, the particle size goes down. And then as the total water content goes down, the particle size goes up. So it turns out the one on the left was a weak tropical cyclone. And the one on the right was a tropical MCS that was pretty garden variety. So what do you call weak and what do you call strong? It just seems like different modes of convection. The way that microphysics behaves deep inside convection could be fundamentally different. And I have absolutely no idea why that would be the case. Does it have to do with the spatial scale of vertical uplift, how it's organized, or is there something else going on? Or did one of these cases get really lucky with a bunch of aerosol, or was there something else happening? I think there's some really interesting questions here.
Where did you say the tropical MCS is? And why are you saying it's weak? I think like MCSs have typically more lightning than like tropical cyclones.
Yeah.
So I guess I wouldn't think in terms of updrafts.
That's a great point. Yeah, I put it in quotes.
That's just because you're thinking people think tropical cyclones are strong?
Yes. Yeah.
Okay.
And maybe we shouldn't think of it that way. Maybe actually the vertical velocity are so slow that they allow for this depositional growth versus, say, aggregation or other things operating within the cloud.
Well, you live very close to a moist
Yeah, I mean, honestly, I'm not an expert in this, but I think this is fascinating why we see such a different microphysical response here in these two different cases. And it may offer some clues for us to maybe hunt down different types of convective features and then maybe separate the statistics out from, say, tropical cyclones versus different types of MCSs over the ocean or over land.
Is that a land or ocean MCS?
Oh, these are both ocean.
They're both ocean.
Yeah, around Indonesia, a little bit north of the equator. Yeah.
I once did a study of this about 30 years ago.
Mm-hmm.
And I was actually studying nuclear winter at the time and why some clouds would be scavenged more than others, depending on their strength.
Yeah.
And what I found was that the stronger clouds are scavenged less, and you get more humidity up high.
Oh.
And the reason for that is the stronger clouds have less opportunity for coalescence, that the lesser strong clouds collect more water as the bigger particles fall, and they sweep out the cloud droplets. But the stronger clouds carry the cloud droplets up high, and then you get a Bergeron mechanism that freezes the ice at the expense of the cloud droplets, and it disappears. And at the same time, the ice gets greater, and that may make bigger particles.
Oh, that's fascinating. Maybe that's the answer.
I don't know, but that's what I found 30 years ago when I studied it.
Did you publish it?
Yeah, well, it's in. I'll tell you where it is, but
Okay,
it's in a book. But yeah, I
Okay,
published it.
I'm very interested to read
Yeah.
that. Anything on simulations of microphysics within deep convection, I think would be illuminating for why we see OPC. Okay, so I got about 20 minutes. So the cloud effective radius is usually larger by a few microns with higher rain rates. So these are matches with AMSR-E and AMSR-2 rain rate. And note that AIRS does not retrieve a profile of effective radius through cloud. So each little data point that goes into each line that you see here is a single retrieval. So there could be a lot more retrievals down here, a lot more retrievals here. I'll show you in the next slide. There's a histogram of the counts that I think really matters to the story. But the bottom line is that the higher the rain rate, the larger the particle size is at the top of the cloud by about 3 to 5 microns. So that's interesting. If you look at, say, surface temperature versus the ice cloud top temperature, so this would be more representative of the deep tropics. This is maybe in the subtropics and mid-latitudes. And I've divided things up into non-opaque versus opaque clouds. And I use that effective cloud fraction to divide the two. So anything larger than about 0.95 goes in the right, and anything less than that goes to the left. And there's no multi-layered clouds in here, so I filtered for those. What you notice for a given ice cloud top temperature and surface temperature, the particles are larger in this convective cloud, okay? So that's also interesting. And it seems like they get larger with warmer surface temperatures. Now what about column water vapor? Again, same story. Thin clouds here on the left, convective clouds on the right, and you see, again, as the column water vapor values go up, the particles get quite a bit larger. There's a slight little increase if you go this way towards higher column water vapor values, and it could be that in the statistical average, this may matter more because there are way more counts over here than there are here on the right. But again, it's almost like you could pick any variable related to climate change, and you know the surface temperature is going up, you know the column water vapor is going up, you could get a larger particle size associated with that. So it seems like everything correlates with an increasing cloud effective radius. So are the rates of sampling changing, or are the values of the cloud effective radii changing within each cloud type? My short answer is yes. If you look at the upper panel, this is trends in the cloud optical thickness. So this is sort of a convolution of the thinness of the cloud and also the counts. And what you see here, it's sort of not focused here in the mid-latitudes, but if you look here in the tropics, you could see the cloud optical thickness has decreased over the last 14, actually this version is a 16-year plot. And, you know, again, this inner shading is the 95% confidence interval, and then this lighter outer shading is with the lag 1 autocorrelation, okay? And then within this set of clouds, you see an increasing particle size here in the tropics, okay? But if you look at the thicker clouds, you can see the cloud optical thickness, this trends aren't significant here, at least in the tropics, but you have an increase in the effective radius. So it seems like the effective radius is increasing in thin or thick clouds, but there's some differences in the cloud optical thickness that appeared related to how thin or thick the clouds are in each category, as well as the counts in those categories.
This is the trend with respect to what?
Oh, with respect to the last 16 years of AIRS data, with respect to the average. And everything's
Is this
deseasonalized.
supposed to be a climate change trend? Is that how you're interpreting it, or?
I don't have enough evidence at that point to say this, but it's clearly changed over the last 16 years, and it's global, and I wish I had more modeling results to verify this.
Okay, but the motivation is to look at climate
Definitely
change.
climate change, yeah. So going back to that Chen et al. Paper, they found an increase in particle size in the 2 Kelvin SST perturbation experiment they did with the 14-kilometer version of the Nikon model. And they speculated that because the circulation strength changed in the tropics, it got weaker, that the ratio between homogeneous and heterogeneous nucleation changed in a way that was consistent with larger particle growth. That you basically had fewer particles like winning all the water vapor. But they didn't show the results. I worked with a few others that have run recent simulations with the CAM-5. They have also shown some increases in the particle size in the tropics, but actually very strong decreases in the extratropics and over land. So the global average in the CAM-5 seems to be going down in the same sort of 2 Kelvin SST perturbation experiments. So I think what few model results I've seen that try and represent a climate change experiment seem to have divergent results. And I wish there were more modelers out there working So, I'd argue sort of in the end that the reduction in the sort of the thinness of the ice clouds with respect to what air sees contributes to this increasing cloud effective radius effect through sampling. So basically you have thick clouds, you have thin clouds. If you have fewer thin clouds, or they're getting thinner, then you're going to have more of the thick clouds weighted in your sample. So you could get an increase because of that. I also think it's entirely possible that convective aggregation may be an underlying operating mechanism here. If you have more convective systems that are more aggregated, you might see more of the thicker anvil type clouds, so you might see increases because of that. But this is like pure speculation. I don't have strong evidence for this. And I mean, it sounds like some here in the department are working on these issues, and we might be able to kind of meld minds on this. I'd like to point out that there's some really interesting results in extratropical cyclone composite studies. One paper by Kodama et al. Showed that in a similar 2 Kelvin SST perturbation where they composited mid-latitude cyclones, they showed that the area of ice actually got smaller in the warm frontal region, but the ice water content actually was the same or got slightly larger. But that reduction of ice tended to expose more liquid. Okay? So maybe the particle size changes here are related to these sorts of issues. Okay, so just to wrap things up here for the next 10 to 12 minutes, I want to go to the second part of the story where we're trying to enhance the time component of the satellite soundings. So there's a long history of proximity sondes and how they're used to assess convective mode and intensity in severe weather. And there's just a lot of papers on this. It's, you know, basically like, why are we bothering? People already understand this. Well, so I would argue that AIRS really has, there's a lot of data to be offered out there. And, you know, the CRIS instrument, EASI, these data I think need to be exploited, especially, you know, considering what we need to do with the Dekado Survey recommendations at NASA. Okay, so we summarized some of these results in a recent paper, by the way, if you're interested. Peter Kalmus was the lead author on this. It's in Monthly Weather Review. And so I would also argue that satellite-based hyperspectral sensing as proximity sondes has so far been a mixed success. So, for instance, CAPE from AIRS tends to be underestimated, but SIN is pretty good when you compare to radio sondes. CAPE tends to be unbiased if you actually put in the correct surface temperature. So there's a couple of recent papers, actually the lead authors here at the University of Wisconsin. And others have shown with the surface area that there's rapid changes in CAPE and SIN in the pre-convective environment. And also interesting differentiation between tornadic and non-tornadic supercells. So,
I'm sorry, can you explain what you mean by proximity sondes?
oh, so soundings that are nearest to convection in the environment.
You can't actually sense in the convection, so you're looking at somewhere nearby.
Yeah, it could be like within a meter versus 10 kilometers versus 50 kilometers. So there are different criterion in which to call it a proximity sonde. So if you have a sonde within 5 kilometers, it might show different behavior than, say, 20 kilometers away. And it might depend on the storm node and what have you. So in the context of the AIRS observations, it's basically whatever sounding is closest to that convective element without being in it. But part of the pixel may actually be, so the convective element may actually be in the pixel. So really the information might be coming from only part of the pixel surrounding the convection. So it's a very sort of ambiguous thing I'm discussing here. I might get a little more specific here in a minute or two. Okay, so I think all those previous studies points towards the importance of the time element of thinking about thermodynamics around convection. Time component's very substantial, and I think these sounders have tremendous untapped potential. And I really think we need to work on this problem a little bit harder. And I'm not saying I'm doing it the right way here. We actually did something really simple and dumb, but it seems to work pretty well. So what we did is we took the AIRS level 2 soundings, combined it with high split, and then fed it winds from the 12-kilometer NAM as well as the 32-kilometer NAR reanalysis. So this is the North American regional reanalysis. And we matched these data to Storm Prediction Center reports of large hail, tornado EF scale, and strong wind speeds. Okay, so that's kind of the simple basic approach here. And here's 2 examples of how this works. This severe weather report here was a large hail report in southwestern Oklahoma. That star is the nearest AIRS sounding, so the center of it. So the sounding is actually 45 kilometers in size, so it may actually encompass part of the storm and the environment around it. Okay? And then all these lines you see are back trajectories at different altitudes. So the lower altitude trajectories are here in orange, and then the higher ones are here in green and blue. And then all these stars are different AIRS soundings at that level where the trajectories are matched to. And what we do is we compare this nearest neighbor in the star, which is in red, to all these parcels that are advected forward in time to this single point using simple adiabatic theory. So if there's no cloud and you're subsaturated, you move around parcels like they're dry. If they happen to be ascending, then they might reach the LCL, then you move up a moist adiabatic. But at that point, you just assume the precipitation magically disappears and ends up at the surface. So all we do is move up the moist adiabat above the LCL and a dry adiabat below the LCL. And you could see some interesting enhancement here. So time does matter. The structure of the environment matters a lot. And it depends strongly on your source of winds that you feed into your trajectory model. So I'll just sort of get to the chase here. CAPE tends to be enhanced by about a factor of 2 over these nearest neighbor SONs. If you look at all reports sort of in an ensemble over here, if you look at all tornado and all hail cases, all these green values are literature values. So again, this is in Peter's paper, if you're interested in the details. But what's interesting is you see a little bit more enhancement in the NAM, so it has slightly higher space and time resolution than the NAR, but it depends on the category. So really large hail, there's bigger differences between the two than, say, small hail. Whether that's statistically significant or not, I mean, it's still to be determined because we don't have a lot of matches in space and time. You'd be surprised like how few severe weather reports there are in this database. And there's a lot of reasons why we have dropouts out of the database. Because it's a limited swath. A lot of the trajectories go outside of the swath. There's bad QC soundings. There's a lot of reasons why we can't keep all the data. Okay, bottom line with SIN, you could see a reduction in SIN by about a factor of 2 as well. And then the NAM 12 seems to reduce it even more than the NAR. Okay, so just to briefly summarize, we account for this time gap using trajectory models. We get more realistic convective indices consistent with the literature. There's more separation between wind, hail, tornadoes than with the nearest neighbor, but we don't account for convective storm mode, and we don't account for any merger with the surface. So we don't treat it correctly, and we'd really like to include the effects of soil moisture in the future. So just to sort of jump to what we're doing right now with our latest NOAA project, is instead of going backwards in time, drawing from the swath to make a new nearest neighbor, we're taking the full swath and going forward in time. So this is just an example of what the 600 millibar water vapor will do over a 5-hour period. And you could see some areas become more densely packed, other areas become less densely packed. So you could do this with temperature and water vapor at different levels. And so what we do is we advect these forward in time. They're recombined into new profiles every 30 minutes, and we make a new sounding. And then we do this at half-degree resolution. So we calculate the convective indices for these gridded soundings, and then we get something like this. So this was actually implemented in the AWIPS-2 system for the hazardous weather testbed. We tested this from late April to early June in Norman, Oklahoma, to what I would argue to be mixed success. Some forecasters found it useful, others hated it, and there's a lot of work to be done. There's a blog on the hazardous weather testbed and the results of the experiment online. I'd be happy to send that to you. I don't think I included it here in the slides. Okay, so just going back to the Dekado Survey, we know that the ice cloud effective radius is increasing. This is related to changing sampling, cloud types. Is it because the water vapor is going up? Is it because the world is warming? Is the circulation changing? I think all of these are possible and likely reasons to some extent. Is this good enough for a program of record? Well, I'd argue it depends what we need it for, because we don't know what we're going to have in the future. I'd also argue that there's some promise to improve the time resolution for thermodynamic soundings around convective storms. And we took a really simple approach here, and I'm sure somebody in this audience could do this correctly or in a more advanced fashion. But how to tease out more time information or polar orbiting data is, I think it should be a high priority. Does it improve this vertical and horizontal resolution? Well, I'd argue no, but I don't know, I think Brad showed me some data earlier that suggests maybe we want to think about that. Maybe it would improve the vertical resolution. And I would advocate using the program of record, just as a NASA hack guy, as a guide for new and innovative techniques and analyses. Because, there just aren't enough people and enough dollars to get these things done. And that document is like the Bible for NASA. So if you want NASA money, think about how to leverage this. So that's all I had. Thanks. Sure. Brad.
So just a comment, getting back to our discussion earlier, if you did the back trajectory like you did for the SPC storm report,
Yeah.
but did that over a whole grid,
Yeah.
that'd be the way to get this enhanced resolution. So that's the reverse we're aiming for. Just do that all over the grid instead of just at one point.
So you would suggest doing that for each time increment backwards in time?
And over a high resolution grid. You could do that at 1/10 of a degree, and
Yeah.
you'll enhance certainly horizontal resolution.
Well, we're using the HER now
Yeah.
to do this, so the HER might be, you think it's probably pretty
Sure.
good wins with the HER?
Yeah.
Yeah.
So that's 3 kilometer resolution.
Yeah.
So.
Yeah.
I wanted to get back to your trend in the effective radius.
Yeah.
So you showed a trend in the tropics, but Marissa pointed out early on you showed this very different distribution in the western and eastern Pacific of effective radius.
In the mean state.
Yeah, and couldn't it just be that you're getting some change? I mean, it seems like you might want to pull out whether there's some longitudinal, that one right there.
Yeah.
It seems like without understanding this, it's not very difficult to understand the trend, right?
Yeah.
I agree with that.
Yeah.
Yeah. I think the things that I've been nibbling at have been trying to get at sort of reducing the dimensionality and looking at it in a different space.
Yeah.
And I think there's clearly something there. The particles are larger as the precipitation gets heavier. Particles are larger with more column water vapor.
But here you're seeing a signal that's not associated with that. Like the West
Yes.
Pacific there versus the East Pacific
Yeah.
have similar column water vapor and similar precipitation. But
Yeah.
you're seeing very different effective radius.
Yeah, I mean, it's unfortunate, I didn't include this slide where I took 4 categories of thin to thick cirrus, and I separated this based on the thinnest clouds and the thickest clouds. This is dominated by thin cirrus. If you pull these out, the particles get much, much larger. And it actually, for the thickest cirrus, it's a very uniform distribution over the tropics. So I think really what we're seeing here are sampling effects to first order. Yeah, so we're just mixing apples and oranges here. So this is, yeah, it's a great point. This is really not a signal of convection. This probably is more so a
Well,
signal.
cirrus comes from convection too, right?
Yes, but a lot of that could be in situ formed from gravity waves, far away from convection. Maybe not necessarily just the detrainment.
Sure.
So, I mean, that's another thing is, it's hard to separate, is it the cirrus clouds due to the gravity waves that are also larger, or is it the particles that get lofted up and then detrained within the anvil that are really larger, or is it right at the cores? I don't think we're quite there yet. Yeah, Bob?
You correlated this with SST? It seems very
Yeah.
hard to do, and we
So, well, that's kind of what these plots are. So this is SST actually from the passive microwave from AMSR. You could, and we separated the deepest convective clouds in the right here from the rest of the thin cirrus on the left. And I guess I didn't articulate this very well. These are log scale of counts. So the fact that there's a white area covering most of this histogram space indicates that there's probably an order of magnitude or maybe a factor of 20 more counts in this non-opaque category than there is in the deep convective.
Well, I was thinking in terms of trends. Sort of trends
Oh, so you're thinking of like a regression of particle size versus SST instead of a secular trend. It was just with time. Yeah, no, we haven't gone to that level of detail yet. That's a great suggestion. And we should probably regress it against some other climate indices. Maybe see how it behaves with El Nino. El Nino probably the first order would relate to the SST. Well, we've done a little bit of that. Okay, so there is, okay. Making me think. So I have a spatial pattern of the trend. Diurnal difference. Yes, okay, so here it is. So this is just straight up taking a 16-year time series and seeing what the difference is, right? So Ching Yue in our group has done some regressions against global SST. And she made a few plots for me that I just remembered that I had, that I haven't thought very much about them. She did this with the effective radius. And what you see is a lot of the patterns are pretty similar, but you see some differences here near the date line that suggest there's a decrease in the particle size with respect to increasing global SST. And there's an interesting pattern in this region, but the rest of the tropics, into the mid-latitudes, there's still this general increase everywhere, and then land tends to show this decreasing trend.
Well, you just pointed to the one pool region. Obviously, that has a distinct climatological response.
Yeah, especially how convection behaves out here as you transition from La Nina to El Nino. Yeah, we did see a signature in the microphysics that seemed to be somewhat symmetric on either side of the equator. But I'll have to dig up that plot. I don't have it copy.
The thing that sticks out there is a decrease over land and increase over ocean.
Yeah. So I briefly mentioned the CAM5. The results that I saw for the CAM5 were pretty similar, but the increase was only limited areas of the tropics, and it had much more spatial structure to it. And then there's a decrease in the extratropics, and then strong decreases over land. But if you just looked at the global average trend of the particle size, it would look like they're decreasing. But the patterns were a little more similar than the global trend. Yeah?
What do you attribute this land sea difference to?
Yeah, it's another very good question.
It's kind of striking.
Aerosols.
Yeah.
Surface heat.
Yeah, well, I would say there are surface issues we have not characterized.
Looks like Michelle Phelps' surface heat.
Yeah, I think especially right in here
Not over Asia.
and here, where you expect low emissivities, I think there's some probably real problems with the interpreting the trends and the retrievals. I would say over the eastern U.S., I don't know, why is it still decreasing? Maybe a little bit less. Very good question. So Catherine Nott and I speculated in a paper a few years ago that there might be impacts of aerosols over land. We noticed that in mid-latitude cyclone composites that we're able to get smaller particles and increase the ice detection if the storms are stronger and there were more aerosols being entrained into the mid-latitude cyclones. But it's hard to argue about an aerosol trend explaining this trend.
In the mid-latitude case, you could also be stealing pristine air from the stratosphere at a greater rate in the strong storms than the weaker ones. And that lowers your mixing ratio of all particles, I would guess, right?
So in terms of available water, well, there's definitely lower column water vapors on average at those latitudes of the land.
But fewer sites too for it to condense or freeze on, if there's a lot more stratospheric air in certain parts of the storms.
Yeah, I honestly, I don't know about any sort of strat-trope effects on this. Maybe that is important.
Yeah,
Maybe
or
since
clean
those
on one
towers
side
are
or fluid
overshooting.
on the
Yeah,
other.
that's what we get.
Clean in the descending dry air, polluted in the ascending moist air.
Yeah, so my intent is not to show this as it's a perfect retrieval. I'm still a little hesitant of the land results, but I think some land areas we could probably trust more than others. This is my bottom line right now.
What about the freezing level change?
Freezing level change, perhaps. Or it could be,
Well, why would that be different over land versus over the ocean?
I guess I don't know much about the climatology of the freezing level. Is it higher over land during the summer? Not necessarily.
I mean, it depends on the cloud. Like the whole entire cloud lifetime leading up to the point where it actually reaches the freezing level and sends past it. So that's what Rosenfeld talks about a lot with his changes, is it's all related to the changes in freezing level, in part due to aerosol cloud interactions. But that happens over South America, and we see that South America matches oceanic trends.
Well, that's interesting. I know I've not really thought about the freezing level, but I've certainly thought about the LCL, where you actually get the base of the storm. And there's no question that has an impact on particle size, especially if you have a fairly dry atmosphere with a high convective base, then you have less chance for a few particles to win. In those cases, homogeneous nucleation tends to be dominant, so you end up with a lot of small particles. Remember, I think it was Dan Lindsay who did some retrievals using the shortwave 3.7 and showed that you could get quite a bit smaller particles in the tops of convection here in the high plains versus the eastern U.S., and he attributed that to the height of the LCO. So maybe that comes into play. Yeah, I don't know.
All right, well, I think there's lots to look
Yeah.
at here, so thank
There
you
you
for
go.
a stimulating talk, Brian. Join me in thanking Brian again. And I will just remind everybody, if you do want to follow up on any of these subjects, Brian will be back in town in 3 weeks.
Yeah.
So it's for another meeting, but still, there's probably some time then where you could actually meet and talk,
Yeah.
flesh out some of these ideas.
October 9th and 10th.
9th and 10th.
Yeah.